.x file. Okay, so what does that file contain? See, this date.x file contains, this is it has its own purpose for RPC join utility, but date.x file contains all those functions which I want to develop. Their signatures only. So there are two functions, as I mentioned. One is the binary date. I believe that will be passing on the timestamp, and the string date. I believe that will be passing on this string like a date information. So there are two functions which you want to provide as service. You can provide their name and their input and output. That's about it. So you have to just provide the signatures of the functions. First thing first. Then you will go and do RPC gen. RPC gen stands for RPC generator. You will provide this date.x file as one of the argument, and this -c-n, find out what are the options, what is the purpose of them. But this particular command will actually create rest of the files for you, like a skeleton. Let's just do that now. So I'm actually going outside this RPC demo. Let me just create a folder called live, okay? And let me cp file date.x date.x to live, okay? And okay, what is it? So I will now go to live folder. You know that this is fresh creator, right? And the file I have got is date.x, right? Now what will I do? I'll run this command rpc gen, right? What does it do? You check it. So see, it created few more files for you. Oh, come on. Oh, tree command is not there. I'll have to install this. Okay. So see, I only provided date.x and it actually generated these all files for me. Okay. Out of this, let's just see one at a time. Let's say date svc.c and date server.c. So see, this says please do not edit this file. It was generated using RPC gen. So you can definitely go and check, but don't edit this. And it has to do more about that wrapper and all those things. That diagram goes. So see, there are actually okay. Let's just see again. Here, stop procedure and the actual one, right? So actual one is one which will be editing, okay? But the stop procedure is actually the one which you are seeing. So this particular file, you can think like it's like a stop file, okay? You will not touch this. It is actually has a lot of more API, complex API. But then, what is the next file? So this file date underscore server.c has actually those two functions, whatever you actually provided, and you have to write your logic here. So basically, how it started, you create a .x file, put signatures into it, create this skeleton completely using RPC join. It provides you files. Then you come back and edit the file with your logic. So this is the function body. Okay. Guys, please confirm that we are connected. This is indeed convenient. Atul. Uh, so we are connected, right? So far, so good. Guys, did you see that I showed you the place where you will put the code? Yes. Okay. So this is the place where you will put your logic. Now, what logic we have put, that is what I will show you in the actual place. The same way, you will also have something called date underscore client. So what logic you want in client, that is the main part, okay, here. So mostly in client, you will just make calls, okay. The important thing is your the server part. So let me go to RPC demo and check the date underscore service C file and see, come on, where am I? Okay, the file I am expecting. See, so basically this is the code what I added. Nothing but just a one line, okay? If you see the previous, it was not there. This was not there. It already have this and this, but the intermediate code was not there. I added this, okay? And for this also, the intermediate code was not there. So this is what the logic, I added. If you may still want to confirm, these lines were not there. I'll just say live and then server, come on, date server.c. C is not there, right? I hope we made some point today about RPC, right? We will continue this in Monday Lab 1, and hope you are actually getting something out of my efforts. Uh, it's been 3:30 already, uh, and you might have next lab. I'm not certain. Any questions so far? So, few of you please confirm that RPC demo you understood at least. Okay. Okay. All right. So I'll stop now. We'll resume tomorrow again. Morning we have a lecture.
Good afternoon, all. We have started our day with the neural network, and we are about to end the day with the convolution neural network, that is a deep neural network, right? So, as per our last laboratory discussion, today we'll see the CNN and we'll try to implement a model with the help of CNN. Fine. So, how can we cover the CNN without covering the actual theoretical aspect of neural network? So, for that, the good thing is the CNN. There are some changes at the forwarded. Now there are two ends in the machine learning whenever you consider the neural network. So, one is the forward pass or the forward end, and another one is the backward end or the reverse pass, right? And at the backward end, we are using the gradient descent. Fine. So in today's lecture, we have discussed the forward pass. We have discussed the connection and how the data flow from the particular layer to particular layer, right? And we were about to discuss the backward pass, but we were not able to complete the backward pass and the gradient descent, how it flow from the output to the input. But it doesn't matter, right? Because in today's lab session, we'll try to implement the CNN, and we'll see why that CNN or the deep neural network are different, how the deep neural networks are different than the neural network that are, let's say, the feed forward neural network, right? So, first thing that we'll observe. The second thing that we'll observe is in this deep neural network, once again, we'll use the back propagation. Once again, we'll go with the backward pass. So, that concepts are same, right? But even without knowing that concept, still we can able to complete this particular laboratory. How? How we are going to complete the laboratory even if we don't know the back propagation? Because once again we have the forward pass and the backward pass, right? So thanks to the torch library where we have the gradient computation, right? No need to write the code manually. You need to just write the forward pass. You need to design the network, and that's it. The backward pass will be calculated by the library. Fine, but we'll discuss the backward pass of the neural network, and eventually for the CNN also it will be same. So now, first I will give you the intuition what exactly the CNN, what is the deep neural network, and which things are different from the feed forward neural network, and then we'll switch to the laboratory. And meanwhile, during this discussion, you can download the file, that is AN and CNN IPYNB file, which I already uploaded into lab number 10. And for the ANN code, I have intentionally removed some portion of the ANN code also, right? Because the lab assignment is yet not over. The deadline for the lab assignment of the ANN is yet not over. So I do not want to give it to you right now. Later, if you want, I can provide it. And we have actually discussed that ANN portion in the last laboratory. So you can just remove that code, ANN portion of lab 10, and you can replace it with the ANN of lab 9 that we have discussed in the last laboratory, that is on Thursday. Fine. And parallelly also try to understand the concept of this CNN. And once we understood this particular stuff, then we'll go back to the implementation, where we will discuss the CNN portion only, right? I will not repeat that ANN portion. But yes, we'll once again use the MNIST dataset, and we'll try to find the try to classify the images of MNIST dataset with the help of CNN now instead of AN. Fine. So that would be the aim of this laboratory, right? And I have to complete in this 2 hour session, so we have to go a bit faster, right? So shall we begin? Are we clear with the idea or what we are supposed to do? And meanwhile, while you are understanding this concept, what you are supposed to do, is it clear, everyone? So one quick recap: download the file from the lab number 10, replace the ANN portion of that lab number 10 with the lab number 9 that you have already implemented. Fine. And the CNN portion of the lab 10, keep it as it is, and we'll discuss that CNN portion after discussing what exactly the CNN is. Fine. So to understand the CNN, let's start with the one dimension, right? So basically, you might aware about the scenario that the CNN model are used with the images, and the RNN based model are used with the let's say the LSTM. If I consider the LSTM, which is RNN based model, RNN means recurrent neural network, so which is RNN based model, which is used with the NLP task, right? And these two are the direction of the recent deep learning techniques. Fine. And the CNN means convolutional neural network. Fine. So two terms are together. The one is a convolution operation, another one is a neural network, right? So we are clubbing it together. So one by one, we'll try to understand the convolution, which convolution operations are there, and how the neural network fit into this convolution, right? So let's begin. So first, let's start with the 1D input. So this X is your one-dimensional input. X is your one-dimensional input, and let's assume these are the weight values, right? Similar to our previous calculation, these are the weight values, right? And for the linear computation, what we were doing, we were calculating this X and W, we will multiplying this X and W. Similarly, these two values we are multiplying X1, W1, X2, W2, and so on. So, right? So if I start from the right hand side, W0 will be multiplied with this value, W1 will be multiplied with the second value, and so on, right? And whatever the result, the sum of that result that we are storing in the S matrix, that is 1.80. Fine. Then at the next iteration, what we'll do, we'll keep this weight as it is, and now we will move this particular weight one level next. Fine. So if you consider the second image, where this 0.01 is now multiplied with 1.10, which was previously multiplied with 1. Fine. And now we are able to calculate this second value, that is 1.96. Fine. And so on. And we'll reach up to the end. And so this is a convolution operation that you might aware from your IP subject, right? So this in IP, if you can recall this W, which name you were using in the IP? Is it discussed this convolution operation? Have you heard about the filters? So let's say if I say 3 cross 3 filter, and let's say the filter value are something like this: 1 1 1 1 1 1 and 1 1 1, all are 1, right? So let's assume this 3 cross 3 filter we have, and if I apply this 3 cross 3 filter on image, what do you think, what would be the output image? Which operation you are applying to the output image? Okay, we'll see. I guess it might be discussed, right? Summation of all value in a window. Yeah, that's fine. But which operation is actually applied on the input image so that the output image, which characteristics are there? Whether it's blur? Yes, exactly, blurred, right? Right, good, fine. So that filters, it's similar to the filter, right? So this convolution operation that we are applying over here, it's just in filters, right? And we'll refer it as a kernel over here. Fine. So right now you can say for this very small example of one dimensional data, the kernel size is 7, that is W0 up to the W6. Fine. And what we were doing since, what we were doing in the IP subject, that we were multiplying that particular values, that is the kernel input, with appropriate pixel, and we are summing up that values, right? So if you observe this equation, I hope it's very familiar to you. Right, so this is convolution operation. I am just revising what exactly the convolution operation. You might know this thing better than me, but as a sake of completion, let's just go through the convolution operation. Fine, because the CNN is based on this concept itself. Fine, are we clear up to this point? And one computation is given over here. Let's say the computation of S6. What would be the equation? Fine. So now this X is our input. This W is weight, or you can say that is the kernel, or we can also refer it as a filter, but mostly with the CNN, we'll refer it as a kernel. Right. Now, if we move towards the two-dimensional input, so let's say if this is my input, that is A, B, C, D, E, F, G, H, I, J, K, L. Fine. And let's say the kernel is W, X, Y, Z. So now what we will do, we'll fit this kernel one by one on, you can say, 4 cross 4 grid. Sorry, 2 cross 2 grid. So this W will be multiplied with A, X will be multiplied with B, Y with E, and Z with F. Fine. So in output, the first cell that you will get, it's just a combination of this 4 and 4, 8 values, right? So AW plus EY and plus FZ. Are we clear? Next, this W will be multiplied with B, X will be multiplied with C, Y with F, and Z with G. Fine, and you will get this value. Fine, and you know this stuff, right? So, do you know this tried? Right. So let me know how much you know related to this convolution operation. Do you know this tried? Stride means just nothing but how you are moving that particular window, right? The kernel window, right? And I don't know what exactly you are referring it into the IP subject. So whenever you move it, the kernel window by one value, that means previously we have fitted it to the ABEF. Now we'll fit it to the BCFG, right? So now we can say the stride is 1. And so which name you are using in the IP subject for this stride? Yep, the sliding, but the what should be the range of sliding? That's just the stride, right? So let's say if I want to skip one value and then if I want to jump to the next value, then based on that, the stride will be decided. Fine. So that is the one thing. And second thing, you might probably, you must know that that is the padding, right? So that three things are very important for this convolution operation. Fine. And I hope you can identify how these remaining cells of the outputs are calculated. Fine. Okay. So let's move ahead. So as we are discussing, let's assume this is your input image and this is the kernel, that is 3 cross 3 kernel, and all values are 1. Fine. And the output will be the blur image. Why it's blur image? Because what exactly we were doing? We were replacing the central value. So that means I will put this kernel on, let's say, 3 cross 3 cell, which probably over here. It should be the exact square, but fine, right? So let's assume it should be probably over here, somewhere around here. And I will, as all values are equal and all are 1, so what will happen at the center location, that is at this particular, sorry, at this particular value of your image. So if I draw that grid, so this central pixel, it will be replaced by the average of all these 9 pixels. Fine, and so on, and we'll move this particular stride or we'll move this window by 1, and eventually you will get this blurred image. And I hope it's clear why it's blurred image, because it's an averaging out. Fine. Next, another kind of kernel can be this one, where we have more weightage on the center, and actually we were removing this -1, means we are reducing the surrounding pixel, or you can say the neighbor pixel, and so it will generate this sharpen image. And actually whenever we are using some software like let's say Photoshop, actually they are doing this all operations itself. Fine. So we just have this quick revision of convolution, because if it is not clear in your mind, then it is a bit difficult to understand the CNN network, right? And so on. The another possibility is the edge detector. And I hope in the IP you have learned that this kind of filter is referred as the edge detector. Why? Because this all are 1 and this one is the -8, right? It will nullify the effect. Or you can say whenever there is some edge, or you can say if I consider this portion, then there is some difference of the left hand side and the right hand side. So overall we'll have some output. Otherwise output will be 0. And if all 9 pixels are of same value, the output will be 0. So this kind of filter are used for the edge detection, right? So what we'll do, we'll slide the kernel on full image. That is, let's say, let's assume right now the stride value is 1 only. Fine. So first 3 pixel, 3 cross 3 grid we'll consider. Then we'll move one step ahead. Once again, we'll consider 3 cross 3 and so on up to the end. Right. So we'll able to generate the another image, or you can say another value, and we'll refer this another image or another value as an feature map. what do you think? What about the size of this particular feature map? Can I say that the size of feature map is always same as the size of your input, or it's less, or it's more? Yes, without padding, you can say the size will be less, right? But if you use the padding, then you can extend the size. Fine. But by default, without padding or without applying any operation, without adding any additional cell, the size would be less of the feature map. Fine. And what we'll do in the convolution neural network is we'll have some k number of such feature map. Means on a given image, we'll apply multiple kernels, and rather than multiple, let's say we'll apply k kernel, and all k kernel will generate one single feature map. And hence we have such k feature maps, right? And all feature map have its own values, right? And let's say if it is image representation, so all will represent some different kind of image, right? So if you just recap the previous three slide, where the first feature map was related to the a blur image, the second was related to the sharpen image, and the third one was related to the next category, that is the edge detector. Fine. So at that time we have used three filters, but you can use such k filters. Fine. So I hope it's clear. Fine. So now for the we have made the case for one dimensional as well as two dimensional data, but what about the 3D data? So whenever I say three-dimensional data, that means let's consider the RGB plane. So we have input image, which is n cross m cross you, where d means depth, and if it is RGB image, the depth of the value of d would be 3. Fine. So for this 3D image, once again we'll use 3D filter, and if you multiply 3D image with 3D filter, what do you think? Which kind of output will get? Whether it's 3D, 2D, or 1D? For full image, which kind of feature map you will have? Right. Fine. But whenever we'll, let's say if we have the 3 cross 3, let's assume that our kernel is of size 3 cross 3, and we'll move that kernel from first pixel to the last pixel. We are interested to generate this kind of 2D feature map, right? So this can be a case of this 3D scenario, right? And let's say this input filter and the output, right? And what should be the dimension of that input filter and the output? So consider this term once again similar to the morning session. Let's introduce some terminology. For the input, we'll consider width as W1, height H1, and the depth D1. Right? This stride S, we have introduced this stride S, but what should be the role of that stride S? That we'll see shortly. The number of filter that we are going to use is K. Fine. Then special extent, that is F, means this of your filter would be F cross F. Right. And the depth, yes, that is this width and height, right? And the depth of particular filter is similar to the depth of input. So right now it is similar to the D1. Right, and it will generate this W2, H2, and D2. Okay, first question, how many feature map will have in output with these all terms W1, H1, D1, S, K, F, W2, H2, D2? So how many feature map will have in the output? ક્યાં ખોવાઈ ગયા બધા? Okay, so if you apply the one kernel, how many map you will get? One. How many kernels we have? Kernels, or we can say filters. They are k filters, right? So we can say there will be k such feature map, one for individual kernel. Fine. So now let's design, or let's try to define what will be the dimension of this W2, H2 and D2. Okay, so how many of you are agree with this? W2 is equals to W1 minus F plus 1, where we are assuming there is no padding. So to make it more clear, let me give you an example. Let's say we have 10 cross 10 image as an input, right? And let's assume that the filter size is 3 cross 3. So can you tell me what would be the size of the output image in order to apply this 3 cross 3 filter on this 10 cross 10 image? I assume that the stride is 1 right now. Stride is 1, no padding. So I think I have to represent it by example. So let's see this example. Let's go back and let's see this example. So this input image, which is of the size is right now not same. So probably let's have the another example where we can have some same size. I don't know whether I've included that example or not. This formula calculation of W2 is actually very easy. Let's say input image is 10 cross 10. Fine. So you can consider 10 cross 10 grid. And now the filter is of 3 cross 3. So what generally we'll do, we'll move that 3 cross 3 filter to the throughout the image. Fine. And let's make it more simple. So I guess now you can answer the question. Input is 9 cross 9 and the filter is 3 cross 3. Right? The simplest version. Still confusing? Let's see now. We have to see this image. Fine. So let's consider this example itself. I hope from this example it might be clear. So there are 4 column and 3 rows are there, right? So 3 cross 4 is the size of your input. Fine. And the kernel size is 2 cross 2. Fine. And we are interested to see what should be the size of your output. And so from this diagram you can say the size is 2 cross 3, right? But let's try to derive some formula for this output, that is 2 cross 3. By seeing at the input and the kernel you can identify that. So for this 3 cross 4, what exactly we'll do, we'll first put this kernel on this A, B, C and D. And next we will put it to B, C, F and G. That, and the third time we'll put it to this C, D, G and H. So if you just consider the column, how many column you will have in the output? So can I say that the number of column is always this whatever number of column in the input minus number of column in your kernel? Can I say that? Or something else is missing? Yes, exactly. Plus 1. Right. So this is 4 minus 2 plus 1. So what is 4? That is height, right? So you can say height of your input. So we will represent it by h1. What is this 2? That is the, okay, what is 2? What was naming convention for this 2? I think it's very F, and the last one is the 1. સવારથી થાકી ગયા લાગો છો બધા. And I hope similarly you can find this W1 minus F plus 1 will be the dimension of your width. Fine, it is clear. So this H2 is equals to H1 minus F plus 1 and W2 which is equals to this W1 minus F plus 1. Are we clear from this illustration or from this example? You can try it on some other examples, right? This condition will be satisfied. Fine. Yes. Okay. Yet this is not the final equation. This is not the final value because we haven't considered the stride. We haven't considered the padding. But at least without stride and without padding, I hope it's sorry, with stride is equals to 1 and with the padding, with no padding, this will be the answer. Fine. So exactly the same formula that we have written in the previous slide. W2 is equals to W minus F plus 1. And then finish. Okay. Let's so whenever we apply it, let's say padding is 1 and the kernel is let's 3 cross 3. So padding of size 1 means at every location, that is at we'll add one row over here, we'll add one row at the end, as well as we'll add one column at the end and one column at the beginning. Fine, and let's assume it's in 0 padding. Fine, so everywhere we have the 0 value. And so with 3 cross 3 kernel, the padding of 1 will produce exact input size image. Agree? Fine. So with 5 cross 5 kernel, what should be the best padding value? If I want to have the output as well as input image should be of same size, 2. Fine. So you all know that concept. Fine. So now what would be the new size W would be this plus 2p, right? Whatever is the previous equation plus 2 times padding. Agree? I haven't included examples for this task because I don't want to spend more time on this calculation, right? Because ultimately we want to learn the CNN, not this convolution network. It is not the part of our subject, right? So I hope you better know all this stuff, but for completion, we are just revising this concept. So I hope now this equation is clear, right? 2p. And one more thing, whenever we have a different stride value, then this will be the equation, right? Divided by S. Let's say if in this case, if the S is equals to 2, it will exactly divide your data into the half size. Fine, so just a simple maths, you can do that thing, right? So this is about the convolution operation. Fine. And there are some examples. I will share this particular slide. So there are some examples. I haven't completed that example. So some dimensions are given to you, and you need to find what should be the final dimension of the output. And so we'll not waste our time on that, right? You can just use this particular equation and you can find the final dimension. Else, and let's say the stride is given as 4 and the padding, there is no padding. Fine. Okay, so now with this quick revision of convolution operation, let's see the connection of this convolution operation with the neural network and why it's a convolutional neural network. Fine. So as I've mentioned previously, it's just a combination of convolution operation and the neural network with some modification. And so we'll see which are that modification. But to understand that, let's go back to our image classification problem that we have just solved yesterday. Sorry, not yesterday, Thursday's lab, right? In the Thursday's laboratory with the neural network. So if you can recall what we were doing in that laboratory, we have some input image. Instead of the Taj Mahal, we were having some numbers, right? So but we were some input image, we were flatten that input image, we were given that particular input image to a network will train itself based on the correct class level, right? And it will adjust the parameter. So this scenario, exactly this particular first scenario, we have implemented in our previous laboratory. Fine. So that was the feed forward neural network. So one improvement on that feed forward neural network. So what we have done in that case, so once again, let me repeat it. So we were having an input image. We know what exactly the correct class, whether it's a car, bus, and momentum or the flower. Simply, I will multiply all the pixel value of input image with some random weight initially for the first level with some random weight, and I will observe what is the prediction done by that uh, neural network algorithm. And if it is a wrong prediction, I will adjust the weight, right, by using the concept of backpropagation that we don't know mathematically right now. Right, but we'll shortly know that. But right, from the practical perspective, there is no need of that maths, right? So with the help of the backpropagation, it will update the weight or it will adjust the weight and repeatedly will perform this action, and eventually we'll able to classify the input correctly. Fine, for some with some handsome amount of accuracy. And so this we already know. Now one improvement to that is, instead of feeding this particular image as it is as a feature to a network, let's perform some feature engineering. That is, let's say we'll apply edge detector. Right, on input image, we'll first apply the edge detector. So you can say as a part of pre-processing, we'll apply the edge detection. Whatever is the output of that edge detector algorithm, that will feed to our feed forward neural network. Right, and once again, the remaining portion is same. And so from the input to the output, we have some n number of cell, then we'll perform the, okay, how many cells will be there in the output? How many neurons will be there in the output? For this example, 4, right? So remember that. And how many input dimension? What should be the dimension of input? Whatever is the dimension of your image. Fine. So let's say if it is n cross n, so you will have n cross 3, as it is a color image, n cross 3. Fine. So that is the first result, that is edge detection. Fine. Then eventually what people have started, instead of considering only a single feature, that is, let's say the edge detector, you can use some very good algorithm, and like this shift and the hog. I hope in the IP subject it might be discussed, right? So where depend on the input image, depend on the type of input image, you can apply different kind of algorithm. But one important scenario or one important thing to observe in all three approaches, right now we have discussed these three approaches. So in all three, yes, we'll flatten it out, right? Don't we have to flatten it? We'll flatten it out, right? So not, will not give full image as it is, we'll flatten it out, right? So input will be the vector to a network, input will be the vector, but the size would be the multiplication of all three dimension, right? So it could be n cross m cross 3. Fine. So if you consider all three approaches, in selecting a feature, there is no learning. Right? We are just applying some direct algorithm, let's say the edge detector, or let's say the hog or the shift algorithm, and that's it. Right? The learning is over here in the second half. That is, we have the correct classification, and based on that, we'll train the model, or we'll adjust the weight. Fine. So this particular algorithms, 1, 2, or 3, any of them you consider, it is the machine learning based algorithm, right? So now let me introduce what exactly the difference of machine learning and the deep learning. Fine. Are we clear? All these three are the categorized as machine learning based algorithm. No matter whether you have the full image as it is as a feature, or you apply some feature engineering on the image and you give it to the network. But that is the machine learning. That's not the deep learning. Clear? પેટર્ન આ ક્લિયર કરવા પછી આપણે આગળ કન્વોલ્યુશન કર્યું એ ભૂલી ના જતા કેમ કે we are going to combine that two things. Now the aim of this deep learning algorithm or the deep learning category is, instead of using these handcrafted features or handcrafted kernels, that is I am saying that let's use this hog algorithm, or let's use this edge detector algorithm. So instead of deciding it by your own, let machine itself decide what should be the best kernel. That means your kernel is a parameter of your model, right? So this is a one change between machine learning and the deep learning, the first change, right? So there are two more changes, but the first one is your kernel values are also a tunable parameter. That means machine will change, the algorithm will change that values, right? Parameters. Fine. Is it clear? Okay. And we know that there are n number of kernels. So rather than just choosing, or rather than just training on a single kernel, let's train our model on multiple kernels. In addition to learning the weight for the classifier itself, right? So classifier weight anyhow we have to learn. But along with that, we are also learning the weight, or you can say the value of your kernel. What should be the value? Let's say if it is 2 cross 2 kernel, what should be the values at that 2 cross 3? We can always initialize it with some random value, but lateral machine will tune that value, and that's the main core, or you can say that's the heart of that deep learning model, where you do not have to apply any feature engineering. And so this is the first point. There's a very important difference between the machine learning model and the DL based model. And so as I have discussed that what we can do, we can consider this kernel values as a parameter, and whenever you're applying the back propagation, also modifier, also tune that parameters, right? And one of such network is this CNN, that is convolution neural network. Next, let's see what exactly the difference of this FNN, that is the feed forward neural network, and this convolutional neural network. So for that, if you observe the image classification problem, like the MNIST dataset, assume that our input image is of 4 cross 4 size. Right? So let's say we have this 16 pixel where the width is 4 and the height both are the 4. Right? So we have 4 cross 4 image as an input. Fine. And once we apply it, once we flatten it out, we have 16 entries in input. Right? And we know that there are 10 classes as it's a digit classification MNIST data set. So there are 10 output units or 10 output neurons. Fine. And in between we can have some n number of hidden layers with some different number of or maybe same number of neurons. Fine. Because actually that is the hyperparameter. But the important thing or important point that we are interested to learn over here is, if you consider a single neuron of, let's say, the first hidden layer, we know that there is a connection from all the neurons of the input. That is, there will be 16 connection for the first neuron. And the same practice we'll have for the rest of the neurons from the first hidden layer, right? And similarly for the second hidden layer, we'll have that connections from the first and so on, right? So it is fully dense layer. And so we already know this structure, right? And we are familiar to this particular structure, the dense structure. But now, in the case of convolution layer, one interesting thing or one interesting output is, let's consider this input once again, there is 2. Now, whenever you calculate, let's say if I calculate this h of 1 1 in the output, this h indicates the output, right? So whenever I consider the first cell of the output, what will the dimension of output? Let's say this 1 2 3 4 are is the kernel size. Stride is equals to 1. What will the dimension of output? And assume that there is no padding, right? So it would be 3 cross 3. Right? Everyone getting this? 3 cross 3, why it's 3 cross 3, the output? We are assuming no padding. Stride is equals to 1. And we know what is input size and what's the kernel size. Right? So this first cell is our H11. So whenever you compute this H11, out of this 16 pixels, which pixels are important to you? Let's say this is the first pixel, pixel number 1, this is a pixel number 2, and so on. So in the computation of H11, which pixels are considered out of the 16? Are we considering all 16 pixels? Right, so that will be 1, 2, 5, and 6, right? So this is 3, 4, 5, and 6. Fine. So we'll consider the weight which are associated with this 1, 2, 5, and 6 only. Fine. So just focus on this diagram H11, where we'll have the connection from 1, 2, and 5, 6 only. Does it make sense? And for this H12, once again, the connection will be 3, 4, and 7, 8. Okay, 3, 4, 7, that means stride is equals to 2, right? Is it fine, everyone? So can you find any difference from this particular explanation the second difference between the ANN and the CNN. First difference we have observed in the previous slide, where we have just said that the AN, what exactly the difference of AN and CNN? Well, in the case of ANN, we are supposed to have the feature engineering, and in the case of CNN, it is not needed because we will consider this kernel itself as a parameter. So that was the first difference. The second difference from this slide and from the previous slide that you can identify is whenever we have the feed forward neural network for a particular layer, all the neurons of that layer are connected with all the neurons of previous layer, but that is not the case with this CNN. So that means there are some sparse connection or sparse connectivity. Even if you look at this slide, I guess you can answer the question, right? So for this H11, this H11 is now not dependent on all 16 neurons. It just depends on this 1, 2, 5 and 6 only. Is it clear? देखो आ गया, clear, right? Fine. So this is the second difference. And this third very important difference is the weight sharing. Okay, fine. Before discussing this weight sharing, this sparse connectivity, the advantage of sparse connectivity is mentioned over here. The number of parameters are less. So those who have at least heard about this CNN, from them, how many of you are agreeing with this particular statement? In the CNN, number of parameters are less than the ANN. Agree 1, disagree 0. Write your answer in a comment. Vivek say 1 means agree. બીજા બધા? 1, 1, 1. Okay. So you all guys are agreeing that the number of parameters in CNN are lesser than the ANN, right? I will make sure that this belief you will not have this belief once we conclude this session. In the CNN, in the full CNN, actually the number of parameters are very, very, very large compared to the ANN model. But yes, due to this sparse connectivity, we have less number of connection and we have less number of parameter, but the total number of parameters are many. And so that's why I started the question like, those who are aware about the CNN, how many of them are agreeing to that? And so right now we can say that the number of parameters are less. Previously, there were 16 connection for H11. For H12 also there were 16 connection. Fine. So the dimension of this H is 2 cross 2. So you can say, okay, how many total parameter in the case of ANN? Let's assume the dimension of H is 2 cross 2. How many total parameter were there? Parameters were there with ANN? Can I say 64? And with this CNN, per H11, H12 are connected with 4. So total there are 16 parameters only. Fine. So let's move ahead. the third important observation or the third important change compared to this ANN model is weight sharing. વચ્ચે વચ્ચે ખોવાઈ જાવ છો બધા કે શું થાય છે? સ્પીડ વધારે લાગે છે કે ઓવરલોડ થઈ ગયો છે ઓલરેડી કે શું એક્ઝેક્ટ સ્ટેટસ શું છે? ખોવાઈ જવાય છે, સૂઈ ગયા. આમાં ક્લાસિફાયર કેમ અપ્લાય કરું? 4 ના 4 આન્સર છે. બીજા તો ખબર નહીં ક્યારેક જાગી જાય ને ક્યારેક સૂતા હોય. Actually, this CNN is not in your syllabus, so it's totally fine if you're not able to understand this particular concept, right? So as far as the theoretical exam concerned, I will not ask any question from the CNN. So those who are focused on the examination only, then they can definitely go to sleep, right? But those who really wants to learn this deep learning concept, so just try to focus. I will try to make this thing bit easy, right? And if you stuck somewhere, then just let me know. I will explain, and maybe we can discuss this laboratory with good rather than good depth. We can say we can discuss it with the very abstract view, fine. But at least we should have the view of the CNN, or you should understand what exactly the CNN is, fine. So આગલા બે ડિફરન્સ થોડા થોડા સમજાણા કે કશું જ નહીં? વાર્તા પહેલેથી ચાલુ કરવાની છે કે ચાલશે અત્યારથી આગળ વધારીએ? પહેલેથી means the difference of ANN and the CNN, not from the beginning, that is what is convolution. ચાલશે સર, બતાવો ને. Okay, so the third difference is this weight sharing. For this weight sharing, just consider this first diagram or the first half, where we have 4 connection, right? And as we know that there are 4 connection means 4 weights, right? And similarly, let's consider some other figure, or you can say some other part which might be around over here, and where we have this 4 connection. Once again we will have this 4 parts or 4 values, fine. So the question is whether these 2 values, or you can say whether these 2 kernels are same or they are different. From the name you can say it's the same, but we are interested to know why exactly it's same. So this is kernel 1, this orange part is kernel 1, and this pink part is kernel 2. And now you can say the weights which are associated with the first neuron and the weights which are associated with the last neuron. Actually, that weights are same. So recall your convolution operation that you are doing in IP. What you are doing, let's say you pick some kernel, let's say we are applying the blur operation, the blurring operation, fine. And let's say we have 2 cross 2 kernel, so we'll have 1 1 1 1, right? So we have 2 cross 2 cell, and all that cell will be 1 1 1 1, and we will apply this 4 entry on the first part of my image, or you can say on the first row, first 2 cell, similarly second row, first 2 cell of my image, fine. So at that time the value will be 1 1 1 1. Now whenever we move ahead, whenever we try that window, the sliding window, will we change that value, or are we supposed to change that value? 1 1 1 1 ની બદલે આગળ કંઈક બીજું લઈ લેતા આપણે, fine. So no matter whenever at whichever pixel position you are, always you are going to have that same kernel. That means at this layer, the first hidden layer, how many the first hidden layer will have same kernel value, or you can say this kernel 1 and the kernel 2 are the same, or the values of kernel 1 and kernel 2 are the same whenever you apply it to some 4 cross 4 image, let's say that is 16 image. Fine. Sorry, 16 pixel image. Question: image size is 4 cross 4, kernel is 2 cross 2. How many parameters you need to have, or you will have at the hidden layer 1? Stride is equals to 2. No padding. Excellent. So there are 4 parameters, right? So at hidden layer 1, we just have 4 parameters, thanks to this weight setting. So once again in the convolution, this is the second difference where we are reducing the weight at more level, or you can say at another certain level. Actually, we just have 4 parameters in this 16 image, that is the, or you can say in this 4 cross 4 image with the CNN. Last slide માં આપણે શું કીધું હતું? In this there are 16 parameters, right? But actually this is not 16, it's just an 4. That's it. For the first hidden layer, you just need the 4 parameters only, where consider this ANN, where we have 64 parameters for the first hidden layer, and the 64 is just for a very small image, that is 4 cross 4 image. Right? And hidden layer ni size bhi કેટલી છે? 2 cross 2. Still we need 64 parameters. So I hope now you can compare this 64 with the 4. Right? So these 3 are the key concepts of the CNN, which makes it different than the ANN. Fine. And now next is those who have said that 1 as an answer whenever I ask for that 1-0 question, where the 1 means the CNN will have lesser number of parameters than the ANN. So for them, let's change the statement. CNN will actually have more number of parameters than the ANN, because this 4 parameter આપણે કહી દીધું, ચલો 4 parameter 2 cross 2 બહુ બધા લોકોએ લખ્યું તો નથી, પણ બે લોકોએ લખ્યું છે, વિવેક and કશ્યપ, right? So we just say that there are 2 cross 2 parameters, so 4 parameters are there, right? But that 4 parameters are for one feature map. How many such feature maps we have? As per our notation, how many such feature maps we have? K. Fine. So let's assume there are three such values. Fine. So we have 3 kernels. So this 3 different kernel will have 3 different weights. So for particular kernel, the weight value will be same, but whenever you have the another kernel, will have the different weight. So now I guess we are ready to see what exactly the architecture of this convolution neural network, after understanding this weight setting, after understanding this the parameter values, right? And after understanding the convolution operation. So just focus on this image. So this is an one example of convolution neural network. અને જે લોકોએ કદાચ ભૂલથી બી સર્ચ કર્યું છે ને ક્યાંક ગૂગલમાં કે એમ convolution neural network, you might have seen this kind of image, right, where there are many boxes. So today it's time to learn that boxes, what exactly the meaning of that particular boxes. Fine. થાકી ગયા છો એટલે આ બધું કેલ્ક્યુલેશન અત્યારે નહીં કરું, નહીં કરાવું, જવા દઈએ. Fine. But those who are really interested, I will share this slide, and those who are interested, so just this value, this S means the stride, F means the filter size, so F is equals to 5, that means my filter is 5 cross 5. K means number of filters that we are supposed to have, right? K is equals to 6 means we have 6 filters. P means padding, right? And this param indicates total number of parameter at that layer. Fine. So at least if you know this full form, then whenever you are fresh, then I guess you can calculate this whole stuff, right? So we'll not go into calculation of that because we just want to know what exactly the heart of the CNN, what exactly the CNN. કે કરવું છે calculation? આમાં તો કંઈક કહો, હા કે ના? And I hope total answer are biased towards at least one value, right? Some say yes, some say no, but exactly we should have unequal distribution of answer. Fine. Okay. So let's say if this is an input image which is 32 cross 32, and once again assume that instead of the number now we have the characters, right? Or rather than let's make it number, so let's say we have 1 over here, and so to cope up with our original computation, right? A નથી લખેલો, અહીંયા 1 લખેલું છે. And so the input dimension is 32 cross 32. We know what exactly the output dimension, right? The output dimension is 10. બસ આ બે જ અઘરું, બાકીનું બધું એકદમ easy છે. Now the first convolution layer where k is equals to 6 means we have 6 filters, or you can say 6 kernels, and each of them are of size 5 cross 5. So k is equals to 6, s is equals to 1, f is equals to 5, and p is equals to 0. So if you put this all 4 value in the equation that we have derived, the answer that you will get is 28 cross 28. Fine. As majority of you are saying no, I'm not going into depth of that answer, but you can put these values into that equation. And try Deknilo, even if you can imagine, just try to imagine. Filter છે 5 cross 5 ના, આ K6 ની અત્યારે જરૂર નહીં પડે તમને. Filter size is 5 cross 5. There is no padding. The stride is of 1. Fine. So the 5 cross 5 નો filter અહીંથી apply કરવાનું start કરો. And whenever you reach towards the end, we are supposed to see what exactly a particular parameter, what exactly a particular value. Fine. So you may find that there are such 28 cross 28 connections. Fine. So this first value, which is of size 28 cross 28, will have such 6 layers, or you can say 6 output in the first convolution layer. 6 output where each output is associated with one single kernel. Fine. So the number of parameter of this convolution, once you apply that, then I'm sure that you will come to know that why it exactly 150. So this is the first operation, the convolution operation that we are applying on an image. Fine. And now we will have one another interesting layer referred as the pooling layer. Fine. In the next slide, I will introduce what exactly this pooling operation is. But right now, let's just assume that the pooling is operation which just shrink your output. Generally, you can use it to shrink your output. Fine. And it doesn't need any parameter. Whenever it's a pooling, there is no learning. In a pooling operation, there is no learning. There are no tunable parameter. Fine. Next, the output of pooling layer will give it to one another convolution layer where we have 16 different kernel, and associated with that 16 kernel will have 16 output. Fine. Once again, that output is followed by a pooling layer. Right. And after that, we'll have one more layer referred as the FC layer. And this FC is nothing but can anyone know what is the full form of this FC? વાંચેલું છે ક્યાંક કોઈએ? Excellent. So that is the fully connected layer. And so this FC is a fully connected layer. And we have such two fully connected layer followed by the output layer. Right. And why it's so fully connected? So let's say if there are 120 neurons in this fully connected layer, so all the pixels of this particular pooling layer 2 will have a connection with all 120 pixel of this FC1. Right, so that's exactly the meaning of the FC layer, right? So that's exactly the meaning of fully connected layer, and that we have in our ANN network. Fine. And once again, the second fully connected layer, which is of size 84. So this all 120 are connected with all 84. And બધાનું બધા સાથે connection is 120 are connected with all 84. And previously, all these values from the pooling layer have a connection with all 120 neurons of FC1. And then that output will give to the final layer, that is the output layer, which is of size 10. Once again, there is a full connection between this 84 and 10. Fine. Chalo ek calculation kar le easy. This parameter 850. Can you tell me how this value 850 comes? Hint. Another hint. તમે કમેન્ટમાં જે છેલ્લે લખ્યું છે બધાએ FC fully connected. Exactly. So we have the bias term, right? So the final output would be 850. Equation લખવામાં ભૂલ કરી કે નહીં? 84 into 10 plus bias. Agree, Muktan? 84 plus bias into 10. Right. Fine. So these are the parameter in this particular last layer, and similarly you can calculate the parameter and just observe the number of parameters. If you sum up total number of parameters, I hope now no one can say that the number of parameters are less in the convolution neural network compared to the ANN. And so one bias term in the 84 which generates this particular output, and similarly the scenario with the other layers. Clear so far? Fine. And so now let's just quickly go through this pooling layer, and then I will discuss some architecture which are present right now. We do not have much time, but maybe till 5 I will try to finish this and we'll discuss the lab task. Fine. So the pooling layer operation are very simple. Let's consider the max pooling. Let's assume the 2 cross 2 filter and the stride is equals to 2. So simply from this 2 cross 2 cell, you need to consider the maximum value as it's a max pooling. So this 1458, what is the maximum value? 8. So that will be the output of this first cell. As the stride is equals to 2, next you need to consider this value. 2134, the maximum is 4. Right, and so on. So this is the max pooling operation. And so there are majorly there are three kind of pooling: max pooling, mean pooling, and the average pooling. Where in the case of average pooling, we are calculating average instead of the maximum or the minimum value. Fine. So that is the pooling layer. So the architecture that we have just seen is actually referred as the LANet 5 architecture, which was given around 1980 or 1990. I don't know exactly the year, but it is very old architecture which was used for handwritten character recognition. Let's just quickly see one more thing. That is this particular summary. Just focus on this summary. So for the back propagation, we have just discussed about the forward pass, right? So for back propagation, we can use exactly the same strategy that we actually will use. Right now, practically we have seen that back propagation, but theoretically we haven't seen that. But the same strategy we can use with the CNN also. From the topmost layer, that is from the fully connected layer, will back propagate the error towards the first layer. And using the gradient descent, the same concepts are there, right? And there is one another terminology referred as the dropout. So you can just note down that term dropout, and in your free time you may check that what exactly the dropout, and you can find the similarity of this CNN architecture with that mechanism dropout. And in CNN also this dropout is used, right? So just spend some time if you have on that dropout concept, right? So number of layers. If you are feeling that there are many layers and there are many connections in the previous, so the Google, which is given that Google Net, and before that this VGG Net was very popular, very famous. VGG19 and VGG16. There were two models. So popularly this 19. If you consider this VGG19, there were 19 layers. Google Net architecture, 22 layer. Then this ResNet architecture, there are 152 such layers, right? So now think or imagine about the computation required for the deep neural network. Fine, and this I guess the latest architecture of 2018, but after 2018 we have many more architecture, and probably this 152 is a small number if I consider the current recent architecture, right? I exactly don't know what is the exact number of that current architecture, but yes, it is definitely more than this 152. Fine. So this is the depth, or you can say this is the computation power required of this deep neural network model, right? And that's why it is you can say almost impossible to train the deep neural network on our local computer. Fine. So let's have a quick summary of some architecture, that is LXNet, ZFNet, and VGGNet. Fine. These images are from the original research paper itself, where they have mentioned the dimension and they have also mentioned the total number of parameters. Fine. એટલે આપણે જે બધા 1 લખ્યું હતું ને બધા 0 લખી નાખો પાછા. Total number of parameters are very less than the ANN. Vivek, good. જાગે છે. પ્રિયલ. હજી એક હતું. 3 આન્સર હતા 1 ના. Fine, good. So ZFNet, total number of parameter And I'm not going into the depth of that architecture, right? We do not have that time. But you can just see this number and imagine the depth of this this CNN architecture or deep neural network architecture, and the VGG net. Total parameter is up to you. You are supposed to calculate the total parameter of this. They have just given that for the non-FC layer, these are the parameter. For the FC layer, these are the parameter. But the summation of that would be the number of parameter in the of the total architecture. Fine. Okay, so with this, let's conclude this theoretical discussion and let's just start the practical implementation. So everyone, please switch to the Google Colab and let's start the discussion. Computer in આ પાડે છે. Let's have 5 minutes break. શ્વાસ લઈ લ્યો બધા શાંતિથી. Because as we have a very heavy dose of this CNN, very dense layer or dense network. But I will make sure that practical we'll try to make it more simpler one. And I hope you have downloaded this particular file. So 5 minute break my download karyo. We'll resume the discussion at around 4:56. Ready? Practically implementation of the CNN, or even if you consider the RNN or any other deep neural network, it's very easy and it's very simplest thing thanks to this PyTorch and the TensorFlow and all other libraries. Fine. So last laboratory we have implemented with question mark. Options: A TensorFlow, B PyTorch. હવે તો કહો સાચું પડવાનું 50% ચાન્સ. Yep, with PyTorch, right? So we'll continue with that, and same definition, same program. So the advantage is આગળની બધી વાર્તા કશું આપણે રિપીટ કરવાની જરૂર નથી, right? How we have converted our input image into the tensor, how we have generated the data, then how we were using that SGD, that is stochastic gradient descent, and so on. Simply today, if you have downloaded the program, we are supposed to design the CNN layers only, and then you need to connect that CNN layer, and that's it. આપણે ખાલી forward pass જ કરવાનું છે ને. Backward torch will help, right? It will just calculate that backward using the gradient, right? So no need to worry about it. Gradient में 0 कर दो, calculate करो, and calculate the loss, and then later use that loss to update the gradient. And so 2 to 3 lines for that. And in the backend, definitely the torch implementation is very complex and very difficult to understand. But from our implementation's perspective, what we are supposed to do, we are supposed to design the layers only. Fine. So what we will do, we will design the convolution layer first, followed by the activation of that convolution layer, followed by question mark. હમણાં જ આપણે ડાયાગ્રામ જોયો એમાંથી શું લાગે છે, શું આવશે હવે? Which layer will be there? Okay, how many type of layers that we have seen in the CNN? જબ્બર થાકી ગયા છો આજે બધા. અને કેટલા સ્લો થઈ ગયા છે આપણે, કે મેં સેકન્ડ ક્વેશ્ચન પૂછ્યો ત્યારે ફર્સ્ટ ક્વેશ્ચનના આન્સર આવે છે પુલિંગ પુલિંગ પુલિંગ. Yeah, Saturday evening, but Sunday also we have session, right? And yes, thanks Vivek for recalling that. Tomorrow I will conduct BJ search session so that we can complete the neural network, and maybe on Tuesday or Wednesday my lecture, BJ sir will conduct my lecture, right? એટલે કાલે બેક પ્રોપોગેશન છે, એટલે જે ખરેખર સુઈ ગયા હોય પહેલા ચા પીને પછી લેક્ચર અટેન્ડ કરજો. હવે તો આન્સર તો આપો, વચ્ચે કોઈ કેટલા લેયર હોય? હાઉ મેની ડિફરન્ટ ટાઈપ્સ ઓફ લેયર્સ આર ધેર in CNN? Different types. ખરેખર સેટરડે ઇવનિંગ છે આજે. Yes, three types of layers are there. One is a convolution, another one can be a pooling layer, and the third is the FC, that is fully connected layer. Fine. So what we will design today in lab session, convolution બનાવશું, then we'll have the pooling layer. Once again we'll have the convolution, pooling, convolution, pooling. એ રીતના અમુક layers બનાવશું, and at the end we'll have FC layer, the fully connected layer, right? And પૂછું question next. How can we design that fully connected layer? લાસ્ટ લેબમાં આપણે કરેલું છે. ફુલ્લી કનેક્ટેડ લેયર આપણે બનાવતા હતા. Whenever we have designed the neural network, which function we have used at that time? Can you recall the function? Linear, excellent, right? So we'll use that 3 kind of layer. To design a convolution layer, we'll use this convolution 2D. It is for the 2-dimensional data. Then for this to design the max layer, we'll use this pulling layer, we'll use this max pulling, and for that the function will be the max pull 2D. Fine. And for the linear layer, or you can say for the FC layer, we already know that the linear is already there, right? And along with that, we also need the activation after every convolution operation, right? So let's just see the arguments. Which argument we are supposed to give? One is the input dimension or the input channel. Another one would be the output channel. Right? The third thing is what should be your kernel size. Fine. The next is what should be the stride value. Fine. Next is what should be the padding value. And this other thing, the grouping, and I'm not discussing it in the depth, right? So આપણે આટલું જ ખાલી રાખશું. Input, output, stride, padding, and the kernel size. Fine. But one thing that I want to mention over here is whenever you want to specify the kernel size, it can be a square kernel, that is 2 cross 2, 3 cross 3, 5 cross 5, 4 cross 4, or it can be of a rectangle shape also. Fine. So if you want it to be a square kernel, you can just mention the 1 dimension. That is totally fine. But if it is rectangular kernel, you are supposed to mention 2 dimension compulsory, right? And with this square also you can mention 2 dimension. It's not a rule, right? So you can have 3,3. Fine. So let's see some examples from this particular page of PyTorch. So here one layer is designed with, yes, 5-second break. Here the one layer is designed with 16 input value, 33 output value. The kernel size is 3 cross 3. Excellent. Stride is 2 and no padding, right? We haven't mentioned the padding, so padding would be 0. Right. Another example. This is also possible, right? So you can have unequal sized kernel. So that is, let's say 3 cross 5 kernel. The stride value is also different. So whenever you are jumping the in a particular row, whenever you're jumping, it should be of 2, but whenever you're skipping the column, you can also skip the column which is of 1, right? And similarly for the padding, right? So different padding for row and for the column, and so on. So you can have different combination of that, but for our example, we'll keep it simple. We'll use this kind of structure, right, where the kernel will be the square kernel, stride up versus the circuit stride up, similarly for the padding. Fine. So we'll use the simplest version from this, but yes, this all are the possibilities, different possibilities for this, right? So likewise, using this convolution 2D, we'll design the convolution layer. Done. And using this max pooling, we'll design the max pool, right? So time thoda ocho છે, let's just see the example only. Max pool 2D 3. What do you mean by 3? Yes, so from 3 cross 3, we'll identify what is the maximum value of that 3 cross 3 cell, and that will represent as the next layer, or you can say the output of that max pooling. fine, and the stride value that we are using in this example is 2, fine. So આપણે આ જ use કરવાના છે, so I'm not discussing the other options of this max pooling, fine. Okay, so let's begin. I hope this ANN portion is already there with you, and in the last session we have designed this ANN as well as we have calculated the output of the ANN. Now let's try to create the CNN model, fine. So if you observe, this remaining portion is same as the ANN. આપણે batch size IP, we have specified the number of iteration, we have specified number of epoch, then we have used this tensor data set to bundle the feature and target together, then data loader, fine, and the CNN model, we are creating it as a model, fine. So now only thing that you need to design is the forward pass over here, fine. And in this next you need to design the cross entropy loss. Over here you have to replace it with the cross entropy loss, fine. Cursor start. How about even if the answer is no, then also we are supposed to start, right? So similar to the last laboratory, we will design the layer and then we'll put it together into the forward pass. Fine. So let's just design the layer first. So that is self dot, let's say CNN1, there is the convolution neural network 1, NN dot, let's say input channel. How many input channels? નથી પૂછ્યું, ચલો 1. Input channel 1 છે, right? જે input હતું આપણું, that is 28 cross 28 image MNIST data set, and આપણે flatten out કરીને 1 કરી નાખી. Input channel is 1. Output channel, let's say 16, we are supposed to have that 16 channel in output. Kernel size, let's say 5. Let's keep stride is equals to 1, and let's say padding, there is no padding, fine. Then let's say self dot relu 1, which is equals to neural network dot relu convolution layer ready. પછી next what? Which layer? કેટલા બધા થાકી ગયા છે, કેટલી વાર તો આન્સર આવે છે પુલિંગ ને. સેલ્ફ ડોટ, let's say max pool 1 is equals to neural network dot max pool 2D, and let's say the kernel size is 2, and let's apply it to all without specifying stride. So stride will be 1. ચલો max pool 1 થઈ ગયું. હવે let's say one another convolution neural network followed by ReLU and followed by max. So CNN2, ReLU 2 and max pool 2. Can you guess what will be the input channel size over here? Good. Output channel, let's say they are 32. kernel size is 5, stride is 1, and let's say the padding is also 0. Fine, let's keep it as it is. You can change it, but right now let's keep it as it, right? You can change it, and you can see what will be the output behavior. Fine, and let's have this max pool 2D also will have the same kernel size, that is 2. And let's have a very tiny CNN network with 2 convolution, 2 pooling, followed by a single FC layer. So let's say self dot FC1 એક અને માત્ર એક જ FC છે આપણી પાસે nn dot linear. I hope you can identify why these dimensions are there, right? nn dot linear 32 cross 4 cross 4 comma 10 as we have the 10 output. These are just the layers that we have created, and similar to the last laboratory we have to combine that layer, right? So let's say forward where we have self and x, variable નામ યાદ છે શું રાખતા હતા? Let's use the same name. Out, right? Out is equals to self dot cnn1, input of that is x. Followed by out. Then this result is followed by max. So out is equals to self dot max pool 1. Once again out is equals to self dot cnn2. The input is out itself. Then out is equals to self dot relu2. The input is out itself, followed by pool 2, right? So out is equals to max pool self dot pool 2 out itself, and finally out is equals to self dot fc1. We just have one value over here, and let's say return out. Done. લખ્યું? કોમ્પ્યુટર પ્રોગ્રામર માટે એવું કહેવાય કે જો ટાઈપિંગ કરતા હો ને તો તમારી ઊંઘ ઉડી જાય. સો આઈ હોપ કે અત્યારે બધા જાગે છે. Now next in this CNN model, similar to the previous, હવે બીજું કશું નવું ચેન્જ નથી, right? Similar to the ANN, we have to specify the gradient. So optimizer dot function હતું 0 grade. One thing is remaining, this entropy. Right, that's it. Another code you already have. And so with this, run your program and observe the output, and then observe the timing taken by this CNN model as well as time taken by the ANN model, along with the accuracy produced by this model maybe after 1000 iteration and the accuracy produced by the ANN after 1000 iteration, right? So compare the time as well as the performance of ANN and the CNN, so that uh, after this particular lab you may able to distinguish between the ANN and the CNN. So if all the syntax are correct, then this code should work. If there are no syntactical error, then this must work and we'll able to produce some output. So this is the working of ANN, right? So just observe the performance or just observe the time. You can just use the time also, and you can print the time literal at the end, right? So time taken by this model, maybe let's say for 2000 or 3000 iteration. So there are some error. Which is related to the size. So I guess I have done some mistake in the parameter, the size value that we have specified. Once I will share the updated model with you, and I will resolve the error, and I will also highlight in that shared file. I will also highlight the correction that I have made in that particular file. And yes, with this, let's conclude the laboratory. And I hope you are clear with the architecture as well as the implementation of the architecture in this PyTorch. And similar to the ANN, you just needs to design the layers and you need to combine that layer, right? So this design in the max pool instead of max pool 1, where in the forward function. But with this max pool 1, we are actually referring this version, this layer, max pool 1. And so the layer that we have designed. Similar, this max pool 2 is actually a reference, or you can say we are using this max pool 2. So do I, right? I have also made some mistakes. So I will go through it and okay, so let's conclude this session and make sure that tomorrow is a very important session for this back propagation, which is a popularly used technique to update the parameter with ANN as well as with the CNN. With ANN, we'll discuss that, but the same concept is applicable to the CNN. So we'll not repeat the same thing with this very dense layer, because it is very, very difficult to reach from the topmost layer up to the first layer. Mathematically it may need very large size projector and there may be so many computations, fine. So we'll consider it with the ANN, but once you have that intuition of the ANN, once you are clear with the computation of mathematical computation of ANN, then same logic you can apply with the with this CNN also, right? So with this, let's conclude this laboratory and we'll meet again tomorrow. Thank you. I will share the updated file maybe after 10-15 minutes, fine. Okay.